All right, so what we're looking at now is situations involving charges. And remember that the basic rules that were set up by Ben Franklin is that you have like charges, there's going to be a repulsion between the two. They don't want to stick. Opposite charges then are going to have an attractive force. They want to be pulled in towards one another. It will still obey Newton's third law, but the generalization that we have, Coulomb's law, is K Q1 Q2 over R squared, where Q1 and Q2 are the individual charges. R is the separation between them, and K is that Coulomb's constant. I think we called it Kc last time. For two charges, it's going to be relatively simple. You'd have perhaps a distance here, either that's a known or that's an unknown. You'd have magnitudes of charge Q1 and Q2. It really just becomes plug and chug. You put in the values, you solve for the equation and the unknown. The K, remember, is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared now. So the real trick here is that sometimes the charges are listed as microcoulombs or nanocoulombs, and so metric prefixes become important. Microcoulomb 1 times 10 to the minus 6 coulomb, nanocoulomb 1 times 10 to the minus 9 coulomb. Okay, so I'll leave the simpler examples with just two charges for you to consider. I would like to do a more difficult one, and now that's going to be problem number 20, and this is going to be on page 658. Give you a second to adjust your materials. Probably won't have a calculator present there. In this problem, we have 4 charges set up in a square with sides of length d. And the charges then are going to be Q1, 2, 3, and 4. And 3 of them are negative and 1 is positive. So I'll shade the ones that have the negative charge, and we'll leave the circle one with the positive. It says that Q2 is negative 2 times Q, Q3 is negative 3 times Q, Q4 is negative 4 times Q, and Q1 is plus Q. So they give you the overall Q value as 2.4 microcoulombs. Okay, so watch out that prefix. That might come back to snap at us. All right, distances are 33 centimeters here, 33 centimeters here. And we want to find the net force exerted on the point charge Q2. So that's this one. Now, if we were to draw force vectors, that's right, I said vectors, so those are back. If we were to draw force vectors on this, we would see that the Q2 being a point that could move. I think that's the easiest way to look at it. If we fix Q3, Q4, and Q1, they're stuck, right? So we anchor them. The net force then would be, with these immovable, the net force would be some quantity on Q2. And as you could guess, the ones that are negatively charged are going to repel Q2, but Q1 is going to attract Q2. Well, how does one approach that problem? Well, I think the easiest way to look at that is to remember what we did for vectors. So the generalized rules for vectors were, we established a coordinate system. So perhaps at point Q2 there, we establish a coordinate system and we're going to make a decision. We're going to make a decision which way is positive and negative. I don't know, maybe this time we want to say to the left is positive. We'll ignore that to the right. And maybe we want to say down is positive. So then at Q2 here, we will then want to find the net force, and the net force is going to be a vector sum. So yeah, again, we'd probably be looking at some kind of a little table, and in that table then we can set up our x and our y coordinates. And we can have our force vector. So then we would have force between 3 and 2 and 2 and 3. Guess what? They're going to be the same because Newton's third law says so. But let's just identify it as F2, 3, and it's going to have an X component. It will not have a Y component, right, based on our system here. And I'm not going to worry about signs yet. I'm going to do the calculations of these numbers. When I put them into the table, then I'm going to put the sign on it. I won't put negative times negative. I'm simply going to find the absolute value of the force between them. And then when I found that force, I will apply it in the table with a sign that's based on our coordinate system for attraction and repulsion. I think that might be the simplest way to do it. If you find a different way and it works for you, then stick with that. For force vector 2, 3. Now, force vector 2, 4 is going to go across that diagonal. And force vector 2, 1 is going to be in the vertical. So automatically we can see that force 2, 3 is only going to have an X component. It's not going to have a Y component. And force 1, 2 is going to have a Y component but not an X component. And force 2, 4 is going to have both X and Y coordinates based on our system. All right, next step then is to calculate those values. So if we want to find force 2, 3, we see that Q2 is negative 2Q, Q3 is negative 3Q. So that simply means 2 times and 3 times in the negative fashion. Remember, right now what I'm going to do is simply the absolute value. I find that simpler to conceptualize. Okay, so F23 is going to be equal to K times Q2, Q3, all over R squared. Remember, the R has to be in meters, and so we're going to have 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Q2 is negative 2, so I'm going to say 2 times 2.4. It's microcoulombs now, so I'm simply going to say times 10 to the minus 6 coulombs. And then Q3 is 3 times, so I'm going to say it's 3 times 2.4 times 10 to the minus 6 coulombs. And then my distance between is 33 centimeters, so I want to make that as 0.33 meters. And then I'll square that. Okay, then again, looking at the unit analysis, we can see that these units start to dump out nicely, and that's going to leave us with a Newton for the final unit. So computing, why don't you check me and see if I'm doing it right. And I'm entering this as 4.8, the second E function, right, for negative 6, times my 3 times 2.4, 7.2, 10 to the minus 6. And then I'll divide that by 0.33 squared. And I'll come up with 2.853 newtons. All right? So that's going to be equal to my F23. Let's put it into the table. Okay, so 2.853, and now based on our coordinate system, this is going to be a repulsion. It's going to be going then to the left. I've assigned that the positive direction, so I'm going to put in 2.85 newtons for my x coordinate on force vector 2, 3. Let's do the other easier one, which is F21. That's going to be our K, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Okay, now it's going to be Q2 again. So that's negative 2 Coulomb, negative 2 times the charge. So again, absolute value, 4.8 times 10 to the minus 6 coulombs. Okay, now Q1, according to our problem, is plus Q. So that's just going to be 2.4. So 2.4 microcoulombs, 10 to the minus 6 coulombs. The distance is the same side of the square, which is 0.33. Okay, so now I'll crunch that out. We'll see what we get. I'm getting 0.951 newtons. Okay, so that's F21 in the y direction. So from here to here, that's going to be an attraction force. So Q2, if Q1 is fixed, Q2 is going to want to move down That's in the positive direction again. So I'm going to put that as 0.951, 0.95 newtons in the Y column. Okay, what's left now is going to be force vector 2, 4. Now, if we cut the diagonal, that's going to make this a 45-degree angle, which means the two legs are going to have exactly the same magnitude, right? So what I need to find is the diagonal distance, and then I'm going to find the components. I just need to find one, say in the x, and then I can find the y because it'll be the same. All right, so first of all, let's find that distance across that diagonal. If this is 0.33 and 0.33, that makes this a 45-degree angle. And if we want to find the hypotenuse h, or we could just, I suppose we just do Pythagoras, that makes perfect sense too. So then h is going to be the square root of 0.33 squared plus 0.33 squared. And some of you math whizzes, I know you're looking at that saying, yep, root 2 times, right? Okay. So it should give us the same result. So I got 0.467 meters. And just for giggles, let's do the root of 2. 0.467. So that would have been faster perhaps, but good practice anyway. 0.467 meters. Okay, I'll redraw that again here. So then we have this point here, and it's going to be 0.467, and that's going to be the diagonal force, a distance, okay, between 2 and 1, 2 and 4, excuse me. Okay, both of those are negative. So F is going to be equal, F24 is going to be equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And then we're going to have our charges. Charge 2, I'll go back to my picture here, is negative 2 microcoulombs, so we'll say 4.8, 10 to my 6 coulombs. Charge 4, Q4 is negative 4Q, so that's going to be what, 9.6 times 10 to the minus 6 Coulomb. I'm doing absolute value again, and this is going to be 0.467 meter, and we'll all square that. Unit conversion cancellations here, leaving us with newtons, so this is looking pretty good so far. All right, so 8.99, 10 to the 9 times 4.8, 10 to my 6 times 9.6, 10 to my 6, divided by 0.467 squared. We're getting 1.899, 1.90 newtons. Okay, so that's the straight line path, right? That's the straight line force. But remember, we're doing it like vector problems, so we're going to find the x and the y coordinates. Looking at this picture again, if 3, 4, and 1 are fixed, then Q4 to 2 is going to be a repulsion, and part of it's going to be in the x direction, so that's a repulsion in the x direction, and it's going to be a repulsion in the y direction. So I need to find out one of the values of the component, so that would be this side, say F24x. So F24x is going to be equal to 1.9 newtons times the cosine of 45 degrees. I want to double check the mode, making sure we're in degree mode as opposed to radian mode. So times cosine of 45, and I get 1.343 newtons. So that's going to be now into our table, 1.343 newtons. And again, we said from 4 to 2 in the x direction, that's going to be a repulsion. that's positive. So 1.343 in the x, call it 1.34 newtons in the x positive. And then our y direction is going to be repelling it upwards, which is opposite to our decided positive direction. And so that's going to be negative newtons. Okay, so now you remember what we do here. We find our resultant vector. So our total resultant force will have components in the x and the y. It's just going to be a sum. Okay, 2.85. And we're going to add 1.34 to that. So 4.19 newtons. And in the y direction, negative 1.34 plus 0.95 is negative 0.39 newtons. Okay, so what does that tell us? It tells us that we're pushing this thing further to the right, and that's going to make sense from the standpoint of these two charges pushing right, and it's the force between 4 and 2 in the vertical is greater than the force from 2 to 1 in the vertical, so that means that its net direction will be upwards for that. So combining those two, remember, our resultant force vector then will look like this. We'll have 4.19 newtons that way. We'll have negative 0.39 or just 0.39 newtons in the upward direction. Remember, the negative is only applicable to our sketch in terms of our coordinate system. So then we can use Pythagorean again on this. Okay. Oop, I did that wrong. Take the square root of that answer that we get. I get 4.21 newtons. And now we're not done, are we? The resultant force is 4.21 newtons, but if you remember, we also have to have a direction with that because it is a vector. Forces are vectors. So that would be the arctangent of 0.39 over 4.19. Should be a small angle, wouldn't you say? And I get 5.32 degrees. Let's see, we'd say maybe above the negative x axis. Well, could you say north of west? I suppose you could. Could you make it relative to the positive x-axis? Sure you could. 174.6 degrees, right? So if we went all the way around here, that would be measured from that position. Okay? So that's sort of a review of what we've done with vectors so far, but it also is reassuring because it tells us that we can use tools that we've developed earlier on in the course to solve problems involving electrical charges. Could we do this with magnetic fields and so forth? Quite possibly, right? And we'll be looking at that as we move forward. So use that as an example. The problem that I'm assigning is number 24, and number 24 is a triangular shape. So similar principles, right? But do read the question and watch out for those micros and centimeter measurements because it will make a difference. Okay, I hope that's helpful.